Hey, Matthew. Sorry,
Hi.
my last class ran a little late.
Can you let my other account in?
Yes, it doesn't show that your other account is trying to join. Oh, there it is. All right, let's zoom in on this integration techniques paper.
All right, now I can hear you from my computer.
Great. 1 second. I need this one. Oh, I have it open in this tab already over here. All right, so let's talk about some of our integration techniques that we were going over earlier for both integration by parts and differentiating under the integral. Actually, before we get too deep into it, I guess I should share my screen. That would help as well. I wanted to recommend a book. So a few weeks ago, before we started talking about integration, I bought this book. I'll put it up and then I'll read its title out loud. Integration for Calculus, Analysis, and Differential Equations by Murat. Let's see, what's his last name again? Murat V. Markin. So I got this book by just typing integration B textbook into Google, something like that. And I just wanted to buy the most highly recommended book, and this was the most highly recommended book, and with pretty good reason. It's a good book. So if you're just interested in this kind of thing, I would definitely recommend this book. We're going to be doing some of the exercise from it today, and but we're going to also finish talking about differentiating under the integral sign, which is actually I don't think is in this book. Let me just check the table of contents one more time. It actually doesn't have it, but it has a lot of other really good techniques and just exercises in it. So we did an example of integration by parts for this kind of integral, and we got a nice formula out of it. And we're going to use that formula. Then we did some examples of power reduction techniques and integrals of inverse trigonometric functions. And then we started discussing a method that Leibniz invented and was also popularized by Richard Feynman, the physicist. And that is called differentiating under the integral sign. So we saw that this diagram commuted, and we can, for sufficiently nice functions, interchange the integral and derivative signs, and that can make our lives easier. So then we saw an example of how we could obtain the gamma function from differentiating under the integral sign. Let me just remind us of how that worked. If we start with this regular integral, this is kind of like the first integral that you would even deal with that would make sense being an improper integral, why you would care about one of the bounds being infinity, because when we plug in infinity into this, we get 0. So if we start with this integral, which in some sense is really natural to consider, and we do a change of variables so that x goes to tx, where t is greater than 0, and we need that condition so that this thing still decays at infinity. Then we get dx is equal to t dx. Oh, there's a mistake right there. That should be dt. And it's purple now. So we divide by t, and we get the factually true statement that the integral from 0 to infinity of e to the tx dx, but there should be a minus sign right here, is equal to 1 over t. So then if we take the t derivative of both sides, then we can obtain the very nice statement that the integral from 0 to infinity of x e to the minus tx dx is equal to 1 over t squared. And as we take the nth derivative, we get that the integral from 0 to infinity of x to the n e to the minus tx dx is equal to n factorial over t to the n plus 1. And if we set t equal to 1, then we obtain an expression for gamma of n plus 1. So the drawback of doing the gamma function this way instead of doing integration by parts is because you don't get the nice recurrence relation that shows us that it would in fact be uh, a factorial type relation for things that are not integers. Um, so that functional equation allows us to extend this to um, uh, non-negative, non-positive real numbers. And so after we saw all this, then I gave 3 special types of integrals. We're going to solve this one first. So the integral from 0 to infinity of e to the minus tx sine of x over x dx. And we can actually solve this in terms of elementary functions. That's pi over 2 minus arctan of t. And we're going to do it with without actually finding an antiderivative of this thing right here. And that's actually a kind of a common trick in a lot of integration problems is you don't find the exact antiderivative. You just show what the answer should be if you plugged the bounds into the antiderivative. And then we can do the same kind of idea on this one, but you actually get something that you need just to invent a new function to describe. So sometimes it's actually not this integral in particular, but the one that we will arrive at, we will see an example of a function defined by an integral. And then we're going to take one more look at this thing, how we could prove it without jumping to polar coordinates, because I don't want to wave my hands too much about how we're integrating, with double integrals and stuff. That is a lot of hand waving going on there. So let's see. Let's rewrite our damped sine integral. And also let's actually rewrite this identity that we derived last time. So the integral from 0 to infinity of e to the minus ax sine of x dx is equal to e to the minus ax times a squared a sine of x minus cosine of x. I'm pretty sure that is what we got. Nope, that should be a 1 plus a squared. So now let's just keep that in mind and write down this integral 0 to infinity e to the minus tx sine of x over x dx. I guess I should explain why it's called a damped sine integral. This is called a damping term because it forces the magnitude of sine to decrease to 0. So let's take the derivative of this thing with respect to t. Sorry, every time I try to scroll down. If we do d dt of this, then we get the integral from 0 to infinity of minus t. That's not correct. So we're taking the derivative with respect to t. So the chain rule tells us that we should get a minus x here, e to the minus tx sine of x over x dx. And that's great for us because the x's cancel. So we get equals minus the integral from 0 to infinity e to the minus tx sine of x dx. So according to our formula, this should be, I'm going to call this function actually f, capital F of t. Come on, Pat. You got it. So this is capital F of t primed. That's going to be equal to e to the minus tx times t should, I guess that should be a minus sign. So we're going to have this thing is oh, we have a minus sign on the outside. Okay. Great. So the minus sign on the outside is going to cancel with the minus sign from the t. So we're just going to have t sine of x, and it's also going to cancel with the minus sign in the cosine over 1 plus t squared. And so now we want to evaluate this thing. I think I might have skipped a step. let's just note, where's the mistake? Oh, we're still evaluating from x equals 0 to infinity. All right, so we're going to have, when we plug it into infinity, this thing is going to stay bounded. And this is going to go to 0. So the value at infinity is going to be 0 minus, if we plug in x is equal to 0, then e to the minus tx becomes 1, and sine of x becomes 0. And then we have cosine of 0 is 1 over 1 plus t squared. And actually, one mistake that I made right here is I also didn't include the minus sign. So we have a minus sign out here. So we get that, just putting it succinctly, f primed of t is equal to 1 over 1 plus t squared. And this is actually much easier to integrate than the thing that we started with, you may or may not notice. We know that the integral of this is arctan up to a constant. And so we need to not constant, it's also not pi. We need to find this constant. So let's just rewrite this here. We have 0 to infinity, e to the minus tx, sine of x over x dx. And this is equal to arctan of t plus c. I still feel like I'm skipping a step. I did this proof like 3 days ago. And then I came home and the Wi-Fi wasn't working. Go away, Zoom. All right, and let's take the limit of this as t goes to 0. So as t goes to 0, this expression, not 0, to infinity. As t goes to infinity, this expression goes to 0. The integral of 0 is 0. So this is equal to 0. And if we take the limit as t goes to infinity of arctan of t plus c, then we get arctan of infinity is going to be pi over 2 plus c and so that is saying 0 is equal to pi over 2 plus c. Let's get rid of this here. Scroll up. So c is equal to pi over 2 minus c, I should say. And I'm pretty sure I made a sign error again. So because if I write what we've got, arctan of t minus pi over 2, I'm pretty sure that differs by what I wrote up here by a sign. Yeah, so where is the sign error? Is it right here? Yeah, I canceled out the minus sign with the sign from this and the sign from this. So there's not a sign here. So there's not a sign here. So we get a minus sign here. So we get a minus sign here. And so our limit should be minus arctan of t plus c, which is equal to minus pi over 2 plus c. So then we get pi over 2 is equal to c. And we can flip this around. Arctan. So yeah, we never found an antiderivative for e to the minus tx over sine of x. Sorry, times sine x over x. But oftentimes in mathematics, you want to be kind of sneaky enough to not do that. So before, what we proved using polar integration is 0 to infinity e to the minus x squared dx is equal to the square root of pi. And a form of this that comes up a lot in statistics and Fourier analysis and a bunch of other places in differential equations is this one. And that's equal to the square root of 2 times pi. And so this thing is an even function. So this is also equivalent to saying e to the minus x squared over 2 dx is equal to square root of pi divided by 2. And so this is the one that we're going to prove now using differentiation under the integral sign. And so when I show you this method, you're going to be kind of like, what the fuck? How did anyone think of this? That's kind of how it went with the polar coordinate proof as well. That's the one that I saw in my class. That is the one that was first historically given by, I think it was Poisson. And I guess we'll call it the Gaussian integral. But there's also some evidence that maybe the Gaussian integral is the only kind of integral that can be solved using polar methods like that. But the method that we're going to do is kind of just like someone really knew how to integrate and they figured this out. So we're going to define a completely new integral. And we're just going to deduce the Gaussian integral as a special case. So we have capital F of t is equal to the integral from 0 to infinity of the quotient e to the minus t squared 1 plus x squared over 2 over 1 plus x squared dx. All right, so before we do any differentiating under the integral sign, I just want to stress that this thing is just designed to have a nice derivative when we do that. So we get, actually, before we do that though, we should note that f of 0 is equal to the integral from 0 to infinity of, this is going to be 0 going away. So we just have dx over 1 plus x squared is equal to arctan of infinity minus arctan of 0, which is equal to pi over 2. Okay, and we're also going to notice that f of infinity is equal to 0 because we're taking a definite integral from a point to itself. So that's 0. So with that in mind, let's take the derivative of this sucker. So I guess I'll just rewrite it down. I'll just abbreviate all this stuff. Let's just make more space. f of 0 is equal to pi over 2. F of infinity is equal to 0. So if you take the derivative of this thing with respect to t, then we get the integral from 0 to infinity of this thing is going to stay the same, except we're going to have a minus 2t times 1 plus x squared over 2 times e to the minus t squared 1 plus x squared over 2. No, let's do this correctly. All right. We're going to have to rewrite it this way. E to the minus t squared over 2 times e to the minus tx squared over 2 over 1 plus x squared. Yeah, I was about to make one of the classic blunders of not using the product rule. So I'll put a d dt out here on the outside. So we get f prime of t is equal to the integral from 0 to infinity of the derivative of this thing is going to be minus t times e to the minus t squared over 2 times e to the minus t x squared over 2 plus e to the minus t squared over 2 times, that's going to be the derivative of this. Okay, all right, Ashes. That's going to be minus tx for the chain rule, and then we have e to the minus tx squared over 2 dx all over 1 plus x squared. No, I wasn't making one of the classic blenders before. I didn't have to do that. I didn't have to do that. All right. This is a very delicate integral or derivative. It's actually not that bad. I have made mistakes doing this integral several times, so I just want to get it right. So we get minus t 1 plus x squared times e to the minus t squared 1 plus x squared over 2 over 1 plus x squared dx. And so if we simplify this, then this cancels with this. And we can pull a minus t out, as well as we're going to have and we can pull this part out. So that's e to the minus t squared. And then what we're left with is 0 to infinity e to the minus tx squared over 2 dx. And let's make a substitution here. I guess I should have left this t on the inside for what I'm about to do. Because let's make the substitution. Oh, I have so much scroll down here. Y equals tx, which implies that dy equals t dx. So we have f primed of t is equal to minus e to the minus t squared, integral from 0 to infinity, e to the minus y squared over 2 dy. And can we integrate this thing? That is the this is the integral that we're trying to compute, right? Let's call it I. So we get f primed of t is equal to, and it's also independent of t is one thing that you should notice. So it's equal to e to the minus t squared times I. And if we integrate from 0 to infinity of this thing dt, 0 to infinity, f primed of t dt equals I minus I times the integral from 0 to infinity of e to the t squared dt. Did I lose a 2 along the way? I did. So let's simplify this side. According to the fundamental theorem of calculus, this is f of infinity minus f of 0. And this is actually, again, the integral that we're looking for I. So we're getting minus I squared. So we get 0 minus pi over 2 is equal to minus I squared. So I is equal to the square root of pi over 2, or the integral from 0 to infinity of e to the minus x squared over 2 dx is equal to the square root of pi over 2. I would really recommend actually writing this proof down, because you're definitely going to see the polar coordinates proof. That the polar coordinates proof is one of the triumphs of polar coordinates beyond just computing volumes of polar shapes or areas of polar shapes. So I'll scroll back up to the top, and I'll let you have a chance to write this down or take screenshots, I guess.
Can you scroll down?
Yep.
Oh wait, can you go up? I missed the big part. Okay. I'm trying to do this by color.
Fair enough. When I first read the paper with this in it, I was like, wow, amazing. I love being able to do things in 2 different ways.
All right, can you go down again? Thank you.
It's the same idea, sort of, as the polar
Oh wait,
equations proof.
I forgot to upload my my third screenshot.
Oh, sorry.
That was on me. Whoops. So this is my fourth. Yeah, can you this one? The one I think. Oh no, go up. Directly under pink. Yeah, this one.
Yeah, so in the polar coordinates proof of this integral, we also ended up computing actually the square of the integral first.
Thank you.
All right, so do you guys want to do some practice for some interesting integration by parts questions? Or do you want to learn how to integrate any ratio of 2 polynomials, assuming that you can factor the bottom one?
Could you say the first one? My dogs are barking.
Just more applications. Just do some practice examples of integration by parts that are kind of more interesting integrals, like practice problems than you would see in your average calculus textbook. So just from this is a great book for integral problems. Or would you rather see how to integrate any rational function, assuming you can factor the denominator?
I'd like to try the second one.
Okay. All
I
right. So,
second that.
yeah, so you can actually always solve these things in terms of arctans, arcsinches, and logarithms, and an integral of a polynomial as well. So assuming you can factor the bottom, then you can always do that. So integral of p of x over q of x dx. And so we're going to make two assumptions. First assumption that is absolutely essential is that we can factor q of x. And the second assumption, which isn't really assumption we have to make, but it also is that the degree of p of x is less than or equal to the degree of q of x. If this is not true, then just use polynomial long division to rewrite this integral p of x over q of x dx as equaling to this integral f of x plus p, let's say p2 of x over q2 of x. So we have to have this condition, but we can always do polynomial long division to put it in this way because we know how to integrate polynomials. Okay, so let's actually just pull a random example from this book because he probably has better examples than I do, but they're all solved the exact same way once you can factor the denominator. And then assuming that you don't want to do a use substitution. Did I skip it? Here we go. Let's see if I can find one that's not going to involve us factoring a degree 4 polynomial. I guess I'm just going to have to come up with one. So let's say we're taking the integral of 4x plus 3 dx over the integral of x minus 1 times x minus 2 times x minus 3. And we'll do this simple one for now. So first thing that we want to do, so who here has seen the method of partial fraction decomposition?
Yes.
Yes. So we're going to want to perform that algorithm. Partial fraction decomposition actually also, even though it seems like you're just solving a system of linear equations. All right, good for you, Ashrith. We are going to do a ton of it. So this method seems like you just end up doing a bunch of linear algebra, but it actually has deep connections to the theory of Taylor series of rational functions, even though you're just doing linear algebra. So our goal, or I should say our sub-goal in this integral, is to rewrite the integrand in this way. So unfortunately, dealing with a system of, an equation like this where we have denominators, it is painful. So let's clear denominators. X minus 2 times x minus 3 plus b times x minus 1 times x minus 3 plus c times x minus 1 times x minus 2. And we want to solve for a, b, and c. So there's actually two ways of doing it. There's one way that doesn't always work, but it is faster. And there's a second way that always works. So we're going to do the way that doesn't always work. It will work in this case, just to show, a sense of when you should know when to take the shortcut. And then we'll do the way that always works, so you're not out of luck when you run into a problem that this won't work. So for this equation, we don't care about the value of x. We just care about what a, b, and c are. So we can substitute any value of x that we want in order to simplify this equation for us. So let's say we set x equal to 1. If x is equal to 1, then what we end up with is 7 is equal to a times minus 1 times minus 3, and then the other two terms vanish. So
We
you
do
get
minus 2.
Yep. And we can do the same thing with x is equal to 2. If we do x is equal to 2, then we get that 11 is equal to b times 1 times 1. So b is equal to 11. And if x is equal to 3, then we get that 15 is equal to c times 1 times 2. So c is equal to 15 over 2. And therefore, we can rewrite our integral of 4x plus 3 dx.
Wouldn't b be negative 11?
Would it be negative 11? Yes, because one of them would be a minus 1. Negative 11. Okay. Times x minus 1 times x minus 2 times x minus 3 is equal to the integral of, that's going to be 7/2 over x minus 1 plus, that should be a minus sign. And yeah, minus 11 over x minus 2 plus, that's going to be 15 over 2 times x minus 3 dx. And all of these are actually logarithmic integrals. I guess I'll write it this way. So this is going to be the natural log of the absolute value of x minus 1 plus, sorry, that's a minus 11 times the natural log of the absolute value of x minus 2 plus 15 over 2 times the natural log of x minus 3 plus c. So let's use this method to find another way of writing the arctan function. Does anyone remember the series that we had for arctan? Let's rederive it. So I'll put c plus arctan.
Wait, so 1 over 1 plus x squared?
Yep.
Okay. I was debating between that or 1 minus.
The minus is arc hyperbolic tangent, but if it was a minus, then we wouldn't have to use a special function for it. Because we could just do partial fractions on that and get an expression involving logarithms. So we can actually do that as well to find a series for arctan or arc hyperbolic tangent, but I'll leave that as a fun and rewarding exercise for you. So we can rewrite this as a geometric series for a sufficient interval of convergence. So we have x squared minus, the absolute value of x squared minus 1 is less than 1. Is that what I want to say? Let's not worry about convergence for now. Let's just find the series. So we can rewrite this as the sum from -1 to the k, where k is going from 0 to infinity of x to the 2k dx. Again, completely ignoring convergence, just focusing on the algebra. We can rewrite this as k equaling 0 to infinity of -1 to the k x to the 2k plus 1 divided by 2k plus 1. And then I guess we'll have a plus c. We don't care about these plus c's. So that is what arctan of x is equal to. We could actually solve for the c this way. We can say that c plus arctan of 0 is equal to 0. So c is equal to 0. So let's use the method of partial fraction decomposition on this. So in the method of partial fraction decomposition, if you run into a 1 over x squared and you don't want to factor over the complex numbers, then you would use your arctan integral. But here we are going to be able to factor it as, I think it's 1/2. Let's just do the partial fraction decomposition. Okay, so 1 over 1 plus x squared is equal to 1 over 1 plus ix times 1 minus ix. So this is a complex analysis proof that we're going to do, but this was one of my favorite just moments in my complex analysis class. So we want that to be written as a over 1 plus ix plus b over 1 minus ix. And so we can solve for a and b as 1 is equal to a times 1 minus ix plus b times 1 minus ix. So I guess before I said we would solve that partial fraction decomposition in 2 ways, the easy way and the way that always works. We did it the easy way here, where you just plug in convenient values of x. Let's do it the way that always works, which is really not that much more difficult because solving linear equations isn't that difficult. So we get 1 is equal to a plus b plus ix times b minus a. So that means that a plus b is equal to 1, and there's no imaginary component here. There's no x component here. So we get b minus a is equal to 0. So b is equal to 1/2, and a is equal to minus 1/2. And so we can rewrite our integral dx over 1 plus x squared is equal to the integral of 1 over 2 times 1 plus I. Oh, wait, I think b was over the minus, right? Yeah, b was over the minus, so we got to make that a minus sign. Minus ix plus, that's a minus sign. 1 over 2 times 1 plus ix dx. So these are logarithmic integrals again. So this is 1/2 times, in parentheses, the log of, that's got to be, why is my mind blanking like this? Log of absolute value of 1 minus ix, absolute value being the complex absolute value, and minus log of absolute value of 1 plus ix. So we get 1/2 log of the absolute value of 1 minus ix over 1 plus ix is another definition of arctan that we could use.
I was able to get your rewarding challenge. Also, what log? Like what base is the log?
For the integral of
For your thing.
dx over x, it's always the log base e.
Okay, that's what I thought. So what? Why didn't you write ln?
Yeah, ln. I guess I should just be writing.
All right. So yeah, I got almost essentially the same thing, except with 1 plus x over 1 minus x,
So
the hyperbolic version.
I put the minus sign with the 1 plus ix.
No. For hyperbolic. I'm
Oh,
not
yeah,
talking
yeah,
about
yeah. That's
yours.
that's cool. I never actually did it for hyperbolic for this one. Um would it be that for hyperbolic? Because
I think so.
for hyperbolic tangent, the derivative is 1 over 1 minus x squared.
Yes. So it factors nicely into 1 minus x and 1 plus x.
Oh, I thought you said there was i's too as well. No, yeah, yeah.
No, I
There's no
said
i's.
nothing
Yeah.
about x.
No i's. But yeah, you would get a very similar expression.
Mhm.
Yeah, arctangent is like people like you have to learn about it in the context of trigonometry to prove all the calculus facts about it. But the real beauty and value of the arctangent lies in what it lets you do for calculus. So assuming that we're not going to go to the complex numbers, because once you start asking questions about complex numbers interacting with integrals, that takes you to the very beautiful field of complex analysis, which we are very unprepared for at this moment. There's a lot of other things that I would have to develop before we could rigorously talk about complex with rigorously, like not even worrying about convergence, just rigorous, a good intuitive way of talking about calculus over the complex numbers. We would need a lot more. But yeah, so let's look at another example where, let's see. All right, Marat, I'll take one of your examples. Did any of you go to Coral Academy of Science?
Both of us.
Did you ever meet Mr. Marat?
Yeah,
I mean,
but not well.
Yeah.
yeah, we never actually like knew him, but we knew he was like a teacher.
Why is that?
Just this guy's name reminds me of him, and I feel like the last time I saw him was like a decade ago. But he's still at Coral, I guess.
Wait. Oh yeah. So does that mean you went to Coral?
I did. I actually went. My 5th grade class at Coral was the first Coral Academy to open in Las Vegas.
I see. Did you ever know someone named Sarah?
Sarah DeSalvo?
No.
Sarah Cinco?
Yes.
Yeah, I know Sarah Cinco.
Wow. That's cool.
Who?
My mom employs her. That's why I ask.
All right, let's integrate this thing. This one, if you're clever, then you don't have to do as much work as and the cleverness here is something that's completely within your range. It's a trick that we've spent a lot of time talking about. Actually, let me make this, sorry, that. Nope, +3. There we go. Plus. Maybe you might get something interesting from this. But never mind. Just integrate this thing for me. I'm trying to come up with a good one. Yeah, this one shouldn't be that bad. Let me see if I can come up with a good one. X squared plus 14x plus 48. I guess these are factoring nicely because I'm making them factor nicely.
You're right. These do feel a tad disingenuous. What is it? Ln x plus 1 minus ln x plus 3.
Yep.
So okay, divided by.
Yeah.
Sorry, I didn't see.
Let's see. I know there's a good example of something that I'm trying to do here where oftentimes it's nicer to treat the denominator with a certain, to rewrite it in a certain way. Ooh, I could come up with some really cruel ones. Yeah, not plus. You got it. Partial fractions without an x in the numerator usually going to have a minus in them.
Yeah, no, I forgot to say my answer times 1/2.
All right, all right. Let me end this with two integrals that are slightly cruel, but you know, it's good tricks. It's a good integration trick. I'm going to give you a second to think about this one. And actually this one as well. These two are difficult for similar reasons. And I'll give you like one more minute to think about, and then I'll show you a way of doing it that may upset you.
For the first one, I'm assuming it has to do with something like tan and sec together.
Yep.
Okay.
So what is the derivative of sec? This is a good hint. What's the derivative?
Secant x times tangent x.
Yep. And this is also a big hint. What's the derivative of tangent?
Sec squared. Yeah. Okay, I see this. I think I do.
I'll even spoil the answer, and you tell me if you can fill in the middle parts. The integral of secant of x dx is equal to.
Oh, I can I try it myself
Yep.
first? Thank you.
All right, all right. If you genuinely figure it out, I would really like to hear what your like thought process was, because I have no idea how someone would come up with this for the first time by themselves, except for just staring really hard at it for a long time.
All right, wait. One hint. It's logarithmic, right?
Yep.
Okay.
Well, just on the very outside. Maybe there's other terms after that.
No, yeah, I don't doubt that. It's
Oh, this should be a minus sign. And this should also be a minus sign.
all right. I've tried multiplication. It didn't work. What is it?
The strategy is actually just to multiply by 1 in a clever way.
Yeah, no, I tried doing that with sec x times tan x plus tan. Oh, I see where this is going. So it's sec squared over tan sec. Okay.
All right. So then what's the next step?
Well, it's over sec x tan x, and one of them is just the derivative.
Actually,
And it is derivative. Yeah,
yep.
the entire thing's the derivative.
So if we set u equal to secant x plus tan x, and du becomes secant squared of x up, but sorry, it should be the other way around. Plus secant x tan x. So then this integral becomes du over u. So we get the natural log of the absolute value of secant of x plus tan of x. All right, so
I should have noticed the common factor, or I did notice, but I just didn't apply it.
yeah, the reason that you wouldn't want to do multiplication is because you have to deal with the product rule, whereas the derivative distributes over addition. So that was really nice. It kind of feels like, honestly, you can prove these things using the quotient rule, but like it kind of feels like these derivatives are this way exactly so that this integration trick will work. But it's really nice. But it also really frustrated me the first time I saw it. And I asked my professor, how are you supposed to know this? And he said, you're supposed to know it by reading it in the textbook. So not very satisfying. But integration is like that. Derivatives are in general much easier to compute than integrals. And like many modern frontiers of science have been defined by our, or I should say their development has only been possible because of our ability to integrate has gotten better. Many parts of science. So yeah, that's all I have for you today. Let's talk about what we're going to talk about in the future. We have way more integration techniques just for partial fractions that we could like state some formal theorems of. And this whole time we have been brushing up against Taylor series a lot. And I want to talk about some of the rigor behind Taylor series, how you know when a Taylor series, like how you know that a Taylor series is actually giving you a good approximation. And I also want to talk about ways that you could get Taylor series in the wild without knowing anything about a limit. Taylor series of like even infinite sums. So just send me an email of like the order that you want to see that stuff in. And There are some integrals that are solvable using more trigonometric functions stuff, like a deeper knowledge of trigonometric functions. But before we get into those, I actually do want to return to the angle identities chapter in our textbook because some of them are important for those trig integrals. So yeah, just email me your thoughts on that. And otherwise, you're free to go.
All right, bye, Ruben. Thank you.
Later, Ashith.
I had a question.
Go for it.
Wait, Asha, if you're like wondering if it's about math, that it's not, or it's kind of. So you know how you helped me come up with like the series in which I'm supposed to, oh, sorry about that. Having dogs is annoying. Anyway,
They just want to be part of the conversation.
all right. Sorry about that. So yeah, you helped me come up with the Davidson thing. How? It's a small question. Do math classes in college usually take a semester or the year?
Semester. It's definitely a semester thing.
I see. Okay, I was assuming they took the year.
So it kind of depends. For instance, my algebra class at UNLV is actually a 4-semester class, but basically there are some classes that will take a year, but you still get credit for doing half a year, and you can stop after half a year.
But would you miss content?
Yes. But in college, sometimes it's more like you don't have time for everything. As a math major, I would recommend that you should take algebra 1 and 2. You should take real analysis 1 and 2. You should take differential equations 1 and 2. But that's just me saying it as someone who really likes all those topics. Actually, I don't like real analysis, but you should still take it. But at some point you're going to have to decide what you're interested in because you literally just won't have enough time to do everything in your undergraduate, at least.
I see. Okay. Well. All right. Yeah, I'll consider that. Thank you.
Yep. All right. Later, Matthew.
Good day.